wasn't prepared. The time has come, the walrus said, to move on to derivatives. Literary illusion. So the theme here, as we talk about calculus starting here, is that you don't want to have to forget everything you learned in single variable calculus. You actually would like to be able to use it. So the goal is going to be introduce new concepts but try to make computations be based, both with derivatives and with integrals, have computations be based on what you already know how to do. So the goal is going to be having made appropriate new definitions have computations based on single variable calculus. Which, so as I said the other day, if you've forgotten how to take derivatives of various sorts of functions, make sure you review. Web work will make you review certain things, but I do hold you responsible for basic calculus skills. And next semester, I'll hold you responsible for basic integrals as well. A couple of them will show up this semester, actually. So I'm just going to concentrate, for purposes of pictures, on functions of two variables. So today we're going to talk only about functions that map R2 to R. And I want to draw you some pictures. So if you think about the graph of such a function, you know, and it doesn't have, it's defined in some domain in R2, but I'm not going to be too precise about that. I'm just going to draw you some sort of generic picture here of some surface, and we're just going to say this surface represents the graph of a function of x and y. And ultimately, what we're interested in, where we're headed by the end of Friday, certainly, maybe faster than that, is understanding what a tangent plane to such a thing would be. But in particular, when we were starting to talk about functions of several variables a few weeks ago, I was trying to get you to think about varying one variable at a time to understand what the surface looked like. So I was trying to suggest that if you were interested in understanding the function, say, at such a point here, say that this is the point A. So again, I'm reminding you, I'm going to use vector A and write its coordinates as AB just to make you frustrated with me. And I'm interested in saying, well, what do slices of this function, this graph, look like as I vary x fixing y and vary y fixing x? So if I imagine fixing the y coordinate here, and remember this is, as usual, the x and the y axes here. So if I vary x fixing y, I'm moving along a line like this. And so I'm imagining slicing the surface with a plane that is cutting the surface, and you see a curve in that plane that goes through my green point. Now, so in that red plane, you're now just down to a function of what? One variable. This is going to be the plane where I'm fixing y equal to b. So I have a copy of the x z plane, but it's sitting over where y is b. Right? So this is the plane where y is b. And in this plane, I have my green point. This is when x is a, right? And I have my point on the graph. and the graph is doing something like that. This curve, remember x is coming out this way, so when I go to the right, I've drawn you a function coming down, so it's coming down as I go to the right.
Why is it a curve? Why is it a curve? Why are we taking that surface?
Well, you would expect if you chop a surface, you slice a surface, you expect to see a curve. As you vary x, fixing y. So as x varies, you get a function of x only. So this graph here is the graph of what function?
XB.
xb. Right? You fixed y. So this is a function just of x. And so you could say to yourself, how do I find, for example, the tangent line, or the slope of the tangent line, to that curve at that point? Take the derivative with respect to the variable, which in this case is x, right? So the slope of this tangent line is, I'll write it in the classical notation for a moment, is d dx of the function x fixing b, y equal to b, and then you're taking the derivative when x is a. Did you guys learn this notation in high school or Calc 1 here?
Yeah.
Yes.
Right, a vertical line saying basically take the derivative at the point x equals a. So officially, if we write down the definition of the derivative, just because we don't want to forget, you're doing f at
A, B.
You're doing a nearby point here, right, where you move over a little bit.
X minus.
So you do x is a plus h, y is still b, minus f at ab over h, and take the limit. Right? That's the slope of this chord here. Taking the limit of that slope as h goes to 0, you're getting the slope of the tangent line. Assuming it exists. Okay, so this limit, assuming it exists, is now going to be, by definition, what we're going to call the partial derivative of f with respect to x. And you get to practice writing new squiggles. So this is sort of like a backwards 6. It's sort of like a backwards 6. We won't ask Mallory how her roommate would write that. She confuses numbers already. So the notation for this is the squiggly sign, and I never remember what it's called. Cameron, do you remember what it's called?
No, sir.
Partial derivative symbol is a...
A funky
No,
D.
it's not.
Yeah,
It's not.
I just think it looks like a D.
It's a funky D.
There is some name, and I've forgotten it, and I'm ashamed of it. But you do the partial derivative. This symbol indicates that you're differentiating with respect to x, fixing the remaining variables. So if we had more than 2 variables, you'd be fixing all of them, except for x, and then you're computing it at the point AB. So that's the notation. It's called partial because you're differentiating with respect to one variable only. And similarly, I could slice the
I have the
surface.
answer, sir. So they call it del D or partial D or partial.
Del.
No, but I thought there was actually a name for the...
Or curly D is one of the official names on the Wikipedia page.
It's del.
No, that's not. There's a different thing that's
I can't
del.
find anything else.
There's a, yeah. Oh. Well, if you, on complex differential forms, it's called the Dolbeau operator.
No, that's not what I want. Right, that's a different meaning. We're not doing that. Much as I love it, we're not doing that in this course. All right, so in the meantime, I'm sitting here with my picture and y feels left out, so to make y feel better, we're going to do the same game and imagine fixing x, varying y, thereby slicing the surface now with a different plane. where x equals a, right? So we have a copy now of the yz plane, and in that we slice the surface, and we see a different curve in this copy of the yz plane. So the companion picture is going to be a copy of the yz plane. Sitting where x is a, and in that plane I now have a curve going through my green point. This is now y equals b, whatever b happens to be. I have my green point and my curve doing whatever it's doing. And I again can talk about the tangent line to it, and it would have slope, oh gosh, that's terrible. Terrible, terrible, terrible. And it would have slope given by, we're just going to call it partial. Partial f with respect to y at the point AB, where I'm sure you can use your imagination and have the definition. Similarly, the y partial so please do try, I know it takes practice writing these curly D's, but it's important in your brain to make sure you distinguish between it and a regular D, because they are conceptually very different, as you will see later next semester. So this is going to be, again, derivative. Now here I'm using regular D because I have a function just of y. I'm fixing x equal a and looking at the function as y varies. And of course I can write that down as a limit as well. Maybe I'll use a different letter like k for varying the y. So I'm going to move over to b plus k here and do the same slope of the chord game that we did earlier. So x is a, y is b plus k, minus f of a, b, all over k. Take that one. Okay. So I assume everyone's sitting here saying, finally something easy that everyone can do. Right?
Yeah.
So for example, suppose we had a function like e to the xy plus 3x to the 5th y squared. Now, if you're going to follow the rules, I'll follow the rules once, and then we'll break the rules to make it easier. Probably easier. Suppose I'm interested in the partial derivative with respect to x at the point AB, where a and b are yet to be specified. Well, so I would take literally what I said up there. Imagine fixing y, differentiate the function that you get by putting in y equal to b. So I'm taking the derivative with respect to x of what function? E to the, all right, so I'll put the b in front. Put the b in for y. All right? Now I take the derivative, and don't forget the chain rule. So we're going to get evaluated at x equals a.
Yeah.
Right, so I'm certainly not expecting you to write it out in terms of limits the way you had to do the first few days in calculus back when. We're not doing that. Unless it's a function where you have to go back to the limit definition. We'll get to that. So what's the answer going to be? B e to the ab, I'm putting it back in alphabetical order, but you don't have to. 15 a to the 4th b squared. And you can all do the y partial just as well as I can. Now, what would be the shortcut that I was referring to Well, you could just think about keeping x and y as variables and just reminding yourself y is a constant. So you could just take this formula and not even say at a particular point, just think of it as a function of x and y. So I'm really doing the partial derivative as a function of x and y. Just take the derivative of this expression with respect to x, treating y as constant. So we've got y e to the xy plus 15x to the fourth y squared. To me, that's easier than doing the step of substituting, and then I can say, well, if I want this at a, b, I'll just plug in a and b. Okay? Okay. However, suppose I were dastardly and I gave you one of our root functions, and you're going to see plenty of these over the next few days. Suppose I gave you something like this function, which we've seen in recent days, right? Suppose we're not at the origin, then it makes sense to divide by x squared plus y squared. And as usual, if we're at the origin, we need to define it. So I'll just say it's 0 at the origin. So this is one of the functions of whom you saw a picture last Friday. Well, now I'm going to ask you, what's the partial with respect to x at the origin? How many of you are going to take this formula and take it with respect to x? How many are going to do it but just won't admit it? That's what I thought. What are you going to do once you've done that? You're going to plug in x and y equals 0, aren't you?
Yeah.
But you aren't admitting it.
No.
No.
Why would we do that?
So if I asked you what's the partial with respect to x at 3, 4, of course you should take this formula and take the derivatives by the quotient rule. But at the origin, you can't do that because at the origin you have to actually use the fact that there's a separate rule for what the function does at the origin and nearby. So the only way to do this, so this is going to come up in homework repeatedly and on the exam, and some of you will do the wrong thing. Please don't do the wrong thing. I'm warning you, and I'll keep warning you. You have to go back to the definition here of taking f at origin plus move x a little bit. So it's h0 minus f at 0, 0 over h. This is different from using this rule at a general x and y, because this rule doesn't make sense at 0, 0. So what do I get when I do this? What is f of h0?
0.
It's 0. This function, if you recall, when we looked at the picture and when we discussed it last week, is 0 on the axes because of the formula for this function. So as you vary x, and as you vary y, this function is 0 everywhere there, because you have y is 0. So it's x times 0 over blah. I don't care. It's 0. And similarly, it's 0 here, because it's 0 times y over blah, which is 0. So what do I get? I get 0 minus 0 over h. And Allison doesn't have to freak out about how the limit doesn't exist. It is not 0 over 0. I'm taking limit of the 0 function, because whenever h is approaching 0, it's not 0. So this quantity is 0 everywhere. And the limit of 0 is 0.
Wait, can you go over how it's not undefined again?
Because when you take limits, you don't actually plug in the
Okay.
thing you're approaching unless it makes sense to plug it in and the function's continuous, right?
Okay.
So you go back to the definition of limit. This is saying, what is this, as h gets smaller and smaller, what number is this approaching? Well, this number is identically 0 for all values of h. And the limit of 0 is 0. So don't try plugging in 0 over 0. That makes no sense. Similarly, but the way to think about it conceptually, guys, is I'm looking at the function along the x-axis. And we've agreed that it's 0 everywhere. It's 0 everywhere out here, and it's 0 at the origin. So along the red axis, it's 0 everywhere. What's the derivative of the 0 function?
0.
Similarly, on the y-axis, you can write down the limit definition, or you can say, I'm taking the function that's 0 for all y and asking what its derivative is at y equals 0. Either way, but you can't just use the original formula. You have to use the rule that defines the function. Okay,
You put an H there where you probably should have been K,
thank you. Thank you very much. Okay.
Is there something special where those limits equal to?
Not necessarily.
Okay.
What you might, do you remember something from our discussion about this function the other day, though? Just, I'm going to make a leading comment here. Anybody planning to be a lawyer? Okay, good. I wouldn't want to be accused of leading the witness here. Leading comment. Was this function continuous? No. Do you remember that as you came in along different lines to the origin, you had different values on those lines? Maybe we did, yeah, I think we did this, but maybe we actually didn't do this exact function.
Oh, it was slightly different.
It was slightly different, so maybe let me actually do it. If you look on the line, so we've said on the axes, it's 0. What about on the line y equals mx? So if I take a line of slope m here, what do I get when I plug in x mx? I get x mx
X squared,
M squared X.
M squared.
and notice you get an x squared in the numerator and an x squared in the denominator.
And m is not equal to 0.
So this function is constant when x isn't 0. It's got value m over 1 plus m squared. For example, when m is a half, what do I have here? That's too hard for you guys.
Yeah.
5/8.
No.
It's
Not like real numbers.
5 over 4.
Excuse me, a half isn't a real number?
Not an integer.
yeah, it's
4 over 10.
So on this line of slope a half, the function is 2/5 there, and then 0 at the origin.
Oh.
Not very continuous, is it? Even on the line, it's not continuous, but it's certainly not continuous as a function on R2. Because you're approaching 0, which is the value of the function at the origin, if you come in on the axes, but if you come in on any other line, your limit is something other than 0, so it's definitely not continuous. So f is definitely not continuous at 0. Why is this mildly surprising?
It's the limit.
It has partial derivatives.
Right, it has partial derivatives, and yet it's not even continuous. harbingers of things to come. What do you remember from basic calculus in one variable? Do you remember some theorem?
It's different.
No, no, no.
It's differentiable, it's continuous.
Right. So our old one variable theorem that says differentiable at a point implies continuous at a point needs revisiting. Something's going on. Partial derivatives, having partial derivatives everywhere seems not to be enough to tell me I'm even continuous. So this is the first warning sign, especially for those of you who've taken some form of multivariable calculus before. You better start paying attention more carefully. Okay. Well, we've looked along the x-axis, we've looked along the y-axis. What do derivatives tell you anyway? Well, they tell you slopes of these slices, but what's the other common scientific interpretation of derivative? Rate of change. So what you can interpret the partial derivative as, for example, here, is the rate at which the function's changing as you move in the x direction, along the x-axis. So the slope here is the instantaneous rate of change as you're moving along the x-axis. This slope is the instantaneous rate of change as you're moving in the y direction. So you can interpret the slopes of these slices also as a rate of change as you move in the direction of the axis along which you're slicing. Well, so for example, if this were the graph of elevation, if this were a map of a hill that you're hiking on, and you were going to hike along the x-axis, or you were going to hike along the y-axis, you would now know at what pitch you're hiking on the hill. The slope of the tangent line is telling you, if you walk in this direction, I'm heading uphill at this rate, or I'm heading downhill at this rate. Now, some of you have actually walked on hills in your lives. Did you always follow the axis?
Yes.
Yes. You conformist. I mean, here you have a map that you're looking at, and this is, x would typically be, if you're looking on a map of the region you're studying or walking on, typically, and you're going to have homework and we'll do examples like this, where x-axis on the map typically represents east, and y-axis going up typically represents north, and then there's west and south. Certainly don't want south. And so what we're discussing here is that if you're at a certain point on the map and you headed due east, then this computation is telling you the rate at which your elevation is changing per unit that you move in the east direction. This is telling you the rate at which your elevation is changing as you move per unit in the north direction. But you might really want to head northeast, or 15 degrees to the north from east, or something like that. And it seems unfair that we only have talked about the slopes we get when we slice along axis directions. Now, if I try to draw something else in this picture, it's going to get really cluttered, so I think I'm going to draw a new picture. But you might similarly want to ask, what is the rate of change of the function, or the slope? Both are useful to think about. If I move in a general direction, not just east or north. So if I move from the point A in the direction of a a vector v. So here I am at the point A still, but now I'm interested in, surely I'm not gonna be successful at drawing the exact wiggly shape correctly. But now I'm interested in proceeding in the direction of some vector v. So in that case, I guess I'm walking slightly southeast or something. Well, couldn't you do the same exact thing and imagine yourself a plane that goes along that line and slices through the surface in that plane? And now you would have a curve, and so if you were walking on the hill and you headed in that direction, instantaneously you'd be walking along this curve on the hill. And you should likewise be curious to know the slope that you're walking at. So now what's the slope here? Well, I can't call it a partial derivative anymore because it's not the x direction or the y direction. So guess what?
We kind of combine.
I'm heading in the direction of v, so let's call it a derivative in the direction of v. The directional derivative of f at a in the direction of v, so that's a lot of words, is defined to be, and I'm going to use this notation, derivative in the direction of v of f at a. Okay? So this encodes all the information, right? Derivative of f in the direction of v, that's the subscript, at a. And what should I do? Well, I should do exactly what we did up there, except I can parameterize, your favorite thing, I can parameterize this line in the xy plane that's through the point A, going in the direction of v. How do I write a point on that line?
A plus
A plus
T.
A plus
Scalar times
scalar tv. So now we have a new letter t, and we'll look at f at a plus tv minus f at a over t. And I should say it's defined to be this, provided the limit exists. Probably your beginning calculus teacher took off a point from you. The definition did say provided the limit exists. At least we have teachers who are mean like that here.
Will you be
Hmm?
Will you be
I'm never mean.
So then yes.
So, well, so we're going to do some calculations of this, but this makes reasonable sense, right? That as you move in this direction, you're seeing at what rate the function's changing, what rate the height is changing on your hill, on your walk. And note, what do I get if I take the derivative in the direction of the standard first basis vector?
Partial derivative.
Yeah, I'm just moving t units to the right. V is at E1, so that's doing A plus T,
T0.
and then B staying the same, right? So this is just the partial derivative at A with respect to x. and similarly E2. So this is a generalization of the partial derivatives. Now I am going to put a warning here. Those of you who have taken some form of multivariable before, be very careful. No formulas that you've ever used are legal yet, and often they will be wrong. So if you have some formula that you have memorized, erase it from your memory. There's another thing that's going to be different, as you're going to see in a few minutes. So let's go back to our example. Let's go back to this example. Conveniently still sitting here. And let's ask, what is, if A is the point to -1, and V is the vector 1, 1, what is the directional derivative in the direction of V of F at A? Well, answer. It's the limit as t goes to 0 of f of a plus tv minus f of a over t. So let's plug that in. I'll come up to the top of the board. F at what point?
2 plus t. So close to half of 3 is 0. And then -1.
Minus f of 2 -1 all over t. Now, at some point, somebody ought to start squealing with pain.
It's just not 3,500 without it.
Hey, no kibitzing. X to the 5th y squared minus f at 2 -1. Oh my goodness.
I didn't know it could be worse than the limit definition of derivatives in one variable, but it is even worse.
Let me finish. 3 times 2 to the 5th. 2 to the 5th is something like 32 times 3 is
96.
96 times 1, thank goodness.
Okay.
All right, how do we do this limit?
You don't.
That's where Nick starts his squealing. How do I do that limit?
Take all the keys.
Do we really want to? Surely there's a better way to do this.
Yeah.
Well, I don't like L'Hopital's rule when you're doing the definition of the derivative, so there's a better, but if your instinct is to do L'Hopital's rule, let's go back and think about this. Is this the derivative of some function of t?
Yes.
Yeah. Sure.
Do we have a better way to take the derivative? So this is if I take f and I compose it with the function that's parameterizing the line, and then take the derivative at t equals 0, I'm doing this exact thing, am I not? So now I'm going to try to use the standard classical derivative notation with a prime when I can. Is this not f of phi of t here? What did I do? I plugged in the point on the line. So this thing is f at phi of t minus f at phi of 0. That's the point A over t. Does that not look like a derivative of the composition? Do you have a better way to compute the derivative of this function of t rather than writing out a limit? Chain rule. It's not so bad, right? No, but clearly, and so for the obnoxious person who wanted to use L'Hopital's rule, that's what you would end up doing.
Yeah.
But how do I do the derivative? Well, it's easy. I have it written down there. This is a function of t. This is the function at 0 over t. So this is the derivative at 0 of this function of t. So all I need is the derivative of f of phi of t, which is this, at t equals 0. Well, even with negative 5 hours of sleep, you guys should be able to do this. Agreed?
Sure.
Huh? No, just take the derivative. So what's the derivative of, call this g of t, I don't know, call it c of t or something. Might as well work on your Greek letters.
Too many Greek.
So how do we do the derivative? Well, we take the derivative and then we're going to plug in t equals 0, right? This is a perfectly nice differentiable function. No problems. How do I take the derivative? Chain rule, product rule, all the stuff you're supposed to know. So what do I get? I get e to the junk times the derivative of junk.
Wait, I thought we were
supposed to use the...
No, what I'm saying is, from the limit definition, we recognize that it is just an old-fashioned single variable derivative. So let's use calculus. Let's certainly not try to do this from the definition of a limit, for God's sake.
2t plus 1.
So I need to take, so you can either multiply this out and then take the derivative, or you can use the product rule. I'm generally more of a fan of the product rule if I can do it. So I'm going to have 2 plus t times the derivative of that, which is 1, plus negative 1 plus t times the derivative of that, which is 1. And then I've got to take the derivative of this stuff. So I have 3 times, again, product rule and chain rule, 5 times 2 plus t to the 4th times the derivative of the inside, which is 1, times what's left over, plus 2 plus t to the 5th times the derivative of this, which is 2 times negative 1 plus t to the 1st times the derivative of the inside, which is 1. All right, I could do 25 minutes of algebra on that. Do I need to? I want the derivative at 0. Let's just plug in t equals 0. So I get e to the
-2
times
2 minus 1.
so times 1.
Go on, do it for me.
1.
1 plus 3 times
5 times 2
5 times 32
5
16.
16 times 1
times
8. Plus
2 to the 5th is
Minus 62.
64
64.
Negative.
No,
minus
this whole thing is 64,
Minus
right?
Times 64.
Times
Times negative.
1, times negative 1.
Alright. So that's 80 minus 64, so that's 16, so that's 48.
Yeah, 16.
So I've got e to the negative 2 plus 3
Yeah,
times
48.
16
89.
5 5 times 6.
48, right? That's the answer. That's the directional derivative in the direction. Okay, that perhaps not the most insightful example to do, but there's a lesson to you on how to do computation slightly more cleverly than complete brute force. Now, I do want to raise a question here. So this, if this were not very realistic perhaps, but if this were the elevation of my mountain, and I were at this point and hiking in that direction, that would be the slope I would be hiking at. Or would it?
Oh my God.
Yes, Matthias?
I'm so copying myself.
No. Is that the slope or is it not the slope?
At that.
This is the rate.
It depends in the direction at that point,
Well, sure.
but not at that point in a different direction.
No, yeah. No, that's fine. But I'm saying I'm at this point A, which I'm not drawing to scale, moving in the direction of this vector V, which in this case was 1, 1. Suppose I took the vector 2, 2. I'd still be hiking in the same direction, would I not?
You would.
But what do you think would happen to this computation if my vector V had been 2, 2 instead of 1, 1?
Something would double.
There, you have 2t everywhere.
And the derivative by the chain rule would be double. I'll actually do that calculation for you on Friday. But you would have gotten double the answer. Well, think about it. What you're doing is you're saying, I'm walking with this velocity vector. And I'm asking myself,
So,
at what rate am I climbing?
yeah. If you're walking faster.
If I walk twice as
On the
fast
same hill. You're
on the same hill, I'm going uphill twice as fast. So, back to Matthias's groan a minute ago. If I really wanted the slope of that hill and not the rate at which I'm climbing,
You need a unit vector.
I need a unit
So
vector.
you're dividing by square root of 2.
So, and again, those of you who've seen multivariable should have been trained when you had some formula that we'll get to soon, that you always had to apply that formula with a unit vector. So if the comment is going to be, and I'll come back to this again on Friday a bit, the comment is, if you want slope, as opposed to rate of change, you need to make sure that your velocity, your instantaneous velocity is 1. And then for every step you take, you're doing rise over run, because you're moving at 1 unit of speed.
So do we divide that by the square root of 2?
Yeah, so if you wanted the slope, you would have to make this a unit vector, which would end up dividing the result by 1, by a square root of 2. So we'll pick up with this and move on to discuss what derivative means on Friday.